Okay, we're going to go over waves and optics practice final exam. Let me get right into it. 13 problems. So, number one, a wave on a stretch spring is described by y of xt equals 0.040 sine of 6x minus 48t, where x and y are in meters and t is in seconds. Determine the amplitude, wavelength, frequency, and wave speed. So, right here we have given our function standard form right here, and then from there what we could just go ahead and do is identify the amplitude, which is 0.040. Okay, our k value is going to be 6 radians, and our angular frequency 48 radians per second, or w there. So amplitude is 0.040. Wavelength calculation right there is k equals 2 pi over lambda, and that's going to be 2 pi over 6. So what we're going to wind up getting is our lambda is 1.047 meters. Okay, that represents our wavelength. And going to our frequency, angular frequency here, our frequency 2 pi f. So our angle, our f equals w over 2 pi. F equals 48 over 2 pi equals 7.64 hertz. And I apologize if I misspeak anywhere. If I'm going too fast, I'm just trying to get you through this video as quickly as possible. All the steps are most of the steps are there in the explanation. So, and the wave speed, v equals 7.64 times 1.047. Okay, we're just wave speed. We're just taking the product of the frequency and the wavelength, and we get approximately 8 meters per second. Okay, so for part B, in which direction is the wave traveling? Wave of the form sine of kx minus that wt. Well, where's that going? That's going to go in the positive x direction. Okay, now building on that, let's see what we have here. Transverse velocity. So find the maximum transverse speed of a point on the string. Okay, so we're going to take that partial derivative for the velocity of y, so dy dt, partial derivative of y with respect to t, and we just substitute in after we take the derivative, so the derivative is negative 0.040 times 48 times the cosine of 6x minus 48t, that quantity. Substitute in here, and the maximum value occurs when the cosine is 1. So this v sub y max, that's 1.92 meters per second. Okay, so that's the transverse velocity. Let's move along to the second one here. Okay, so second one, we have a string of length 1.8 meters is fixed at both ends. The wave speed on the string is 120 meters per second. Find the fundamental frequency. So for part A, the standing waves on a wire, given L is 1.8 meters, V is 120 meters per second. So for a string fixed at both ends, we're going to use F sub n equals NV over 2L. Fundamental frequency for n equals 1 is F sub 1 equals 120 over 2 times 1.80. You're just substituting and simplifying. We get F sub 1 is fundamental frequencies 33.3 hertz. For letter B, find the frequencies of the second. So the second and third harmonics, the second harmonic is going to be F sub 2 equals 2 F sub 1. So F sub 2 equals 67.7 hertz. The third harmonic, F sub 3 equals 3 F sub 1. So F sub 3 equals 100 hertz. And now we can move along to letter C. If the string vibrates at 200 hertz, determine whether a standing wave is produced. So the allowed frequencies are F sub n equals n times the quantity 33.3. We check that, just substitute our values that we know, 200 over that 33.3, we get about 6. So since this is essentially an integer, 200 hertz corresponds to the 6th harmonic. So yes, we could say a standing wave is produced. Okay, that's number 2. Moving along to number 3. train moving at 32 meters per second blows a whistle with frequency 540 hertz. What frequency is heard by a stationary observer as the train approaches? So for letter A, that's Doppler effect. So let's see what we're given. The source speed is 32 meters per second. That's V sub S. Source frequency is F equals 540 hertz. Speed of sound, V equals 343 meters per second. So we have to use the approaching observer formula for a moving source, so that F prime there equals F times the quantity V over V minus the source speed. So F prime, just substitute, equals 540 times the quantity 343 over 343 minus 32, and we wind up with 595 hertz. For the receding observer, it's going to be the sum instead of the difference in the denominator. So the receding observer formula is F prime equals F times the V over V plus V sub S. Substitute what we know, we get 494 hertz. So that's for letter B, the frequency heard after the train passes and moves away. That's the receding observer. And for letter C, explain physically why the observed frequency changes. We could say the following. So the physical explanation: as the train approaches, sound wave fronts bunch together, decreasing wavelength and increasing observer frequency. As the train moves away, wave fronts spread apart, increasing wavelength and decreasing observed frequency. Okay, so that is number 3. Moving along to number 4. Going through this quickly because you could have this as a reference. And I assume you're done with the course or you've studied it independently and for quite a while, and you know a lot of the material. So two speakers emit identical sound waves in phase at frequency 680 hertz. A listener is located so that the path difference from the two speakers is 0.50 meters. So letter A, determine the wavelength of the sound. So for part A, interference of sound, given F equals 680 hertz, path difference is going to be 0.50 meters and velocity 343 meters per second. Okay. Wow. So wavelength, all we have to do, wavelength in this situation is just going to be V over F, 343 over 680. Okay, velocity over the frequency, we get 0.504 meters. Okay, for part B, what will the interference at the listener's position be? Will the interference at the listener's position be constructive or destructive? Okay, so constructive interference occurs when your change in R is equal to M times lambda. So since that value, okay, 0.50 is approximately 0.504, the path difference is essentially one wavelength, okay, in relation to A, one wavelength. So it's constructive interference. Okay, so for part C, what is the smallest path difference that would produce complete destructive interference? So destructive interference would be that change in R, quantity M plus 1/2 times lambda. So the smallest value, lambda R the change in R equals lambda over 2. So lambda R would be 0.504. Okay, that wavelength divided by 2. So the change in R equals 0.252 meters. Okay, that's all for number 4. Moving to number 5. Object is placed 30 centimeters in front of a converging lens of focal length 12 centimeters. Use the thin lens equation. So find the image distancing. That's part A. Well, thin lens image distance, we're given that D naught is 30 centimeters and your F is 12 centimeters. So all we're going to do is set up the equation in fraction form. It's going to be 1 over that 12, 1 over F equals 1 over the 30, 1 over D naught. okay, and plus 1 over d sub I. And then just solving. 60s are LCD. We wind up with 60 over d sub I equals 3. And then we wind up with isolating d sub I equals 20 centimeters. That's our image distancing. Part B. Well, is it real or virtual? Well, it's positive. Positive image distance means a real image. Part C. Find the magnification. We'll use m equals negative d sub I over d naught, or d sub 0, d naught, whichever. M equals negative 20 over 30. You get negative 2/3. So our magnification here is a negative 0.667. So what does that mean? So state whether the image is upright or inverted. So basically, off of letter C, it's a negative magnification, so the image is inverted. Okay, so going quickly through these. Number 6. Concave mirror has a radius of curvature 80 centimeters. Use the mirror equation, find the focal length. So, part A, the spherical mirrors, given the radius is 80 centimeters, focal length for spherical mirrors is just F equals R over 2. So we get 80 over 2, F equals 40 centimeters. Okay, the image distance, we're going to use the mirror equation. Set this up as 1 over 40. So let me read part B. Sorry about that. An object is placed 50 centimeters from the mirror. Determine the image distance. Okay, so image distance, use the mirror equation. So from information from part A, where it's going to be 1 over 40, 1 over F equals 1 over 50, okay, and plus 1 over d sub I, okay. And solving for d sub I, we get 200 centimeters. Magnification, again, m equals negative d sub I over d naught. So that's negative 200 over 50. We get negative 4, so negative magnification. So if we want to describe the image, we could say it's a real image, okay, because we have a positive d sub I. It's inverted because we have negative magnification, and in relation to that magnification, it's enlarged by a factor of 4. Okay, so moving forward, that's number 6. Let's go to number 7. Okay, light travels from a glass and n equals 1.52 into air. Calculate the critical angle. So refraction and total internal reflection. Dealing with the critical angle. For part A, we use sine of theta sub c. That equals n sub 2 over n sub 1. So that's just going to be 1 over 1.00 over 1.52. And taking the inverse sine of that, we're going to get theta sub c is equal to 41.1 degrees for our critical angle. Okay, so letter B. If the incident angle inside the glass is 50 degrees, determine whether total internal reflection occurs. So, does TIR occur? Total internal reflection. So the incident angle is 50 degrees. That's greater than 41.1 degrees. That's larger than the critical angle. So since it's larger, we could say yes, total internal reflection does occur. Part C, explain why total internal reflection cannot occur when light travels from air into glass. Well, total internal reflection only occurs when light travels from higher index to lower index. Air has lower refractive index than glass, so TIR cannot occur going from air into glass. All right, that's 7. Moving along to number 8. Okay, double slit experiment. A double slit apparatus uses light of wavelength 620 nanometers. The slit separation is 0.25 millimeters, and the screen is 2.5 meters away. So for part A, determine the spacing between adjacent bright fringes on the screen. So for part A, here's what we're given. So lambda is 620 wavelength, or 620 nanometers. That would be, in scientific notation, 6.20 times 10 to the negative 7th meters. That's our preferred scientific notation for this. Our D value here, 0.25 millimeters. I'll change that to 2.5 times 10 to the negative fourth meters. And our L will keep as 2.5 meters. So everything's in terms of meters, units of measurement. So our fringe spacing here, which we'll need, is delta Y equals lambda capital L over D. And we just substitute. So that delta Y equals 6.20 times 10 to the negative 7th times 2.5. Sorry, not delta. So that delta Y equals lambda times L over D. Okay. Spoke too fast. Just substitute what we know. And the change in Y. Okay, change in Y is 6.2 times 10 to the negative 3 meters, which is about 6.2 millimeters. Change in Y. That's our spacing. Third bright fringe for letter B. Find the distance from the center to the third bright fringe. So what we do is we do Y sub 3. That's going to be 3 times what we add for our change in Y. So that's just going to be Y sub 3 is 18.6 millimeters. And for letter C, how would the fringe spacing change if the wavelength were decreased? Well, effects of decreasing wavelength, since our change in Y is proportional to our wavelength, our lambda, decreasing wavelength decreases fringe spacing. Okay, so moving along. Number 9. Okay, laser beam of wavelength 520 nanometers passes through a slit of width 4.0 times 10 to the negative 5th meters. A screen is located 3.0 meters away. Letter A, determine the angular position of the first diffraction minimum. So we would do here, list what we're given in scientific notation. Here we can convert this all to scientific notation. You know how to do it. First minimum angle for the minimum, what we would do, A sine theta equals M times lambda. Now, our first minimum here, M equals 1, so that would be sine theta equals lambda over A. So substituting what we know in scientific notation, right? So that lambda, convert those nanometers. So sine theta equals 5.2 times 10 to the negative 7th over 4.0 times 10 to the negative 5th. Sine of theta 0.013. Take inverse sine, you get about 3/4 of a degree for our theta, 0.75. For part B, find the width of central maximum on the screen. So, width of central maximum, the distance to first minimum, y equals L tangent theta. Okay, small angle, your y is approximately capital L times theta. Convert to radians. Theta equals 0.013 radians. So our y value is going to be equal to 3.0 times 0.013. And that's going to give us y is 0.039 meters. So our central width, to determine that, we're going to go ahead and say central width is 2y equals 0.078 meters. And we could write that as 7.8 centimeters. Okay, so from here, let's see what we can do. Would increase, letter C, would increasing the slit width increase or decrease diffraction spreading? So in this situation, a larger slit width decreases your diffraction spreading. So that's more of a textbook notes type thing, understanding diffraction. All right, so number 10. We have unpolarized light with intensity 180. W over m squared passes through two polarizing filters. The angle between the transmission axes is 40 degrees. For part A, find the intensity after the first polarizer. So polarization, we're given that information. After the first polarizer, unpolarized light loses half intensity. So we would say I sub 1 equals I naught, or starting over 2. So I sub 1 equals I naught over 2, right? So that's after the first polarizer. So that's just going to be 180 over 2. We get 90W over M squared. Part B, find the intensity after the second polarizer. So we're going to use Malice's law after the second polarizer. So I is going to be equal to I sub 1 times the cosine squared of theta. Just substitute in there, and you're going to get I equals 52.8 W over M squared. C, explain why the first polarizer reduces the intensity by half. So we could say here, textbook, note stuff. Unpolarized light contains all polarization directions equally. The polarizer transmits only the component aligned with its axis, averaging to half the original intensity. Okay, so moving along now, part number 11. Radio station broadcasts at frequency 99.5 megahertz. Find the wavelength of the radio waves. So we're given what we're given. Convert MHz to hertz. 9.95 times 10 to the 7th. Make sure to convert that first. So wavelength for the EM waves, V equals C. So what we're going to do here, our lambda is going to be equal to just the 3.00 times 10 to the 8th. Divided by 9.95 times 10 to the 7th. And lambda is 3.02 meters. So remember where that 3.00 times 10 to the 8th comes from. Now from here, period. Determine the period of the wave. Use capital T equals 1 over just 9.95 times 10 to the 7th. That's all. It's 1 over the megahertz. And I'm sorry, 1 over the hertz in this situation because it's in hertz. So T equals 1.01 times 10 to the negative 8 S. And for part C, would ultraviolet light have a longer or shorter wavelength than these radio waves explain? Okay, so textbook knowledge required pretty much for this, lecture notes. So ultraviolet light has much higher frequency than radio waves. And since that wavelength is C divided by the F, what we could say is a higher frequency results in shorter wavelength. So ultraviolet light has a much shorter wavelength. Okay. Number 12, we have conceptual portion, 5 questions here. So let's see here, or 5 components. This is all textbook stuff, note stuff that should be studied and known, understood. So conceptual portion A, why can 2 waves pass through each other without permanently changing shape? So for letter A, waves obey the superposition principle. They temporarily overlap, then continue unchanged because the medium responds linearly. Diffraction becomes strong, that's letter A. My apologies. That's letter A. Letter B, why does diffraction become more noticeable when wavelength increases? So now picking up with letter B. Diffraction. Diffraction becomes stronger when wavelength is comparable to opening size. Larger wavelengths bend more around obstacles. Okay. Letter C, explain the difference between a real image and a virtual image. A real image, for letter C, a real image forms where light rays physically converge. A virtual image forms where rays only appear to originate. Letter D, why does blue light refract more strongly than red light in most transparent materials? Well, blue light has shorter wavelength and experiences larger refractive index in most materials, causing greater bending. Letter E, explain why interference patterns demonstrate the wave nature of light. Letter E, interference requires superposition of waves with phase relationships, demonstrating light behaves as a wave. Okay. And for number 13. Okay, we have a soap film. Whoops. We have a soap film, N equals 1.33, its thickness 2.80 nm. White light is incident normally on the film. For part A, determine the wavelength in air that experiences constructive interference in the reflected light. So we're given N equals 1.33, T equals 280 nanometers. Now, just moving over to the right where that's that asterisk, what we could say is usually the lowest visible constructive wavelength is found using M equals 0. So this would give your lambda equals 4n times t. So right here first. Now, if you put that in there, you're going to get lambda equals 1,490 nanometers. Now, this would designate it at infrared and not visible. Okay, so that's why we would go to the next order in this. Instead of starting, well, if we started at m equals 0, we want to go to m equals 1. Okay, so if we use the constructive reflection with one phase reversal, if we do this 2nt equals quantity m plus 1/2 times lambda, if we use m equals 1 and we substitute our values, we're going to get lambda is 497 nanometers. And that is visible. Okay, think about difference between visible and infrared and numerically how they're differentiated in terms of nanometers. So that's letter A. Letter B, would the reflected color shift toward longer or shorter wavelength if the film thickness increase? Okay, would the reflected color shift toward longer or shorter wavelengths if the film thickness increase? Sorry. So this is more of a textbook type thing, application of what you know from textbooks in regards to this topic. So for letter B, the answer would be increasing thickness increases constructive wavelengths, shifting reflected colors toward longer wavelengths. Okay, so that's the entire practice exam. Hopefully it could be a supplement for you studying for your exam. Hopefully this helps a little bit with review, and thank you very much. Have a great day.